Welcome everybody to the panel, the future of programming. We've been doing these panels since as long as I have been involved in the PDC, maybe even before that. But today we have a very, very, very special panel with all the big shots of Microsoft. So here we have Don Box. I don't think Don needs an introduction, everybody knows him. Then here we have Jeffrey Snover. Anybody that's using PowerShell, thank Jeffrey. Butler Lampson, a legend. You know, the internet wouldn't be there without him. One of the many inventors of the internet. Herb Sutter.
We couldn't get out more.
Yes. If you love native code, Herb is your friend. And then last not but least, we have, Burton Smith, Mr. Supercomputer. Also, we're going to do an experiment today, so you can send your questions and remarks to a #PDC panel, a #PDC 2009 panel. And what I will do is I will pick and choose questions to direct them to the audience. So you are really kind of influencing how this panel is kind of moving. All right? So let's, but I want to start by giving the panelists an opportunity to express, you know, what problem they think is the most important that we face today. So let's start with Burton. So Burton, what keeps you awake at night?
Well, what keeps me awake at night is how are we going to write parallel programs?
Good. And Herb?
That. And how are we going to deal with people constantly taking dependencies they don't understand?
Okay, good.
Well, I was going to say concurrency, and then I was going to say dependability, but actually, those are kind of stereotype, boring things that everybody says. So I'm going to say making it possible for users of rich applications to program them. And don't tell me that we already have Visual Basic for that.
Yeah, so what keeps me up at night is figuring out how to provide a widest dynamic range possible, where like people who are real simple can get in and do what they need to do simply, and then the experts can do that as well and have one language to do that so that you have a rich ecosystem of people working together.
Perfect. And Don?
I spend every night wondering how am I going to make developers fall in love with the database. You know, there's millennia worth of value in there that, you know, we keep wanting to put a prophylactic over so that we don't get tainted by it. And it turns out there's some really good stuff in there, and how do we make that viable?
Okay, perfect. So I have a mic already. So let's kind of now give Don the opportunity to answer my next question, because what we heard here is two interesting things. There's concurrency and parallel programming, and then there is normal programmers. So the question is it possible for normal programmers, people like you and me, you know, not guys with small heads, not with big heads, to do parallel programming? Don, can I write parallel programs? And what are you going to do to help me to do that without running into deadlocks and...
I think the jury's out. The world is doing a lot of experimentation. There's a lot of interesting language work out there. People are doing Erlang. We're doing a lot of stuff inside of Microsoft. I'm not a visionary on this one. I have no idea. Someone's going to build something. I'm going to say, oh man, I want that thing, and I'm going to go use it. So.
Okay.
How can you be asking this question, Eric? You solve this problem with Link.
Well, but
anybody can write parallel programs. It's easy.
Okay, good. Well, so the problem is solved, but I'm not so sure that I believe that.
Well, try Link first, and don't think about anything else unless it proves to be inadequate. My slogan for parallel programming is stripe, stream, or struggle.
Okay, but that's a good question. So what you're saying is that if your program, and if I can interpret your answer, if your program is amendable to kind of natural decomposition, then it's easy. But are all problems that easy, Herb?
No, and we're making it easier to write parallel code. Now we just need to write correct parallel code. That would be the nice next thing. but it's important to understand that we're now as an industry doing for concurrency and parallelism what we already did for GUIs and what we already did for objects. They've been around for decades before in niche markets. You wanted to write a GUI, Hello World was 3 pages. Now we're bringing it to the mainstream, and what we're seeing today is that first wave of technologies like the VB version 1, the MFC version 1s, those kinds of things coming out, and we're just riding that wave where the tools still need to be built. So what we have now is better, it'll still get better.
And Burton, so you are kind of, really, you have been here in the industry for a long, long time. So is there anything that, we as young kids can learn from, your experience? Like you've been doing parallel programming for I don't know how long. What are we missing? What are we forgetting as young kids?
Well, I'm not sure there's a lot we're forgetting. There's been a lot of work done, and of course many of us are doomed to reinvent things that that have existed. But the new insight, I'm going to talk about at 3 o'clock actually, which is what to do about state and how can we address that. I think if we write in functional style with SQL, for example, or with Excel, we can run those things in parallel without much muss or fuss from the programmer. The challenging thing is what happens when you want to maintain state. So the title of my talk is The State of Parallel Programming. This is a plug, right? And it's not about the situation of parallel programming. It's about how to deal with state in parallel. And what's interesting is that understanding that has emerged over the last few years. It's not something we knew back in the day. It's kind of a fairly recent collection of insights. So I think there's very promising opportunities ahead of us for doing that. And so anyway, so I'm not too depressed by the current situation at all. I think we can make progress on this one.
So talking about state, and there was one question here, and Don was talking about databases. What about transactions? Are transactions the silver bullet? Software transactions or database transactions the silver bullet to solve all our problems with locking and stuff like that?
No.
Yeah.
No. Good.
But transactions are great where they work. In fact, Jim Gray explained this to me about 10 or 15 years ago. Transactions are like fairy dust. A COBOL programmer writes a piece of business logic. It's a sequential program. It does some relatively simple state transformation. And then you sprinkle transaction fairy dust on it, and automatically it becomes parallel, it becomes fault tolerant, and it becomes load balanced. We don't have anything else like that anywhere in computing. The next closest thing actually is Link and its providers like Dryad. It's just remarkable, but of course it only works for that class of problem, where you can decompose it into these sequential chunks that the COBOL programmer can work on. There's lots of other problems where that's just doesn't address the need.
So Don?
Look, I think transactions certainly have a role to play. What's interesting is I went a couple years ago to PLDI, where they had a day-long transactions workshop. It was very interesting. I came from the Jim Gray school, which was, at least my variation of it is very much pessimistic concurrency, lock-based transaction, standard 4 isolation levels. That's the way I learned transactions as a younger person. And it was really interesting to hear the language folks and the hardware folks, which is who was at PLDI, who very much had kind of the multi-version concurrency control slant. And when we talk about STMs, you could implement an STM using pessimistic concurrency control, but people aren't doing it. And so I've, over the last couple of years, really kind of, transactions in a much less firm term in my head, because people use it in so many different ways, unfortunately.
Yeah, but the semantics is the same, right? Whether you use optimistic or pessimistic concurrency control.
For the most part, yes. Yeah, the problem is that the devil's in the details. But what's interesting is I think the MVCC stuff
I see it both in the programming in the small. So like Clojure, which is kind of the current alpha geek language du jour, has I think probably one of the best treatments of STM integrated into the language and into the libraries. But if I look at the kind of programming in the large, right, and I look at the web and the way the web-based protocols work, right, it turns out if you look at an E-tag, it's the way we do optimistic concurrency control on the web. And so there's something going on kind of at this extreme and at this extreme, and I don't think we've kind of figured out how to close the entire loop. At least I haven't. But I think it's a fun time to be in this part of the industry.
Burton?
Yeah, I view transactions not as the province of database exclusively. In fact, it's an important abstraction. All it really means is that updates are done atomically and in isolation. The question is, what should the domain of the update be? And like I say, 3 o'clock.
Let me just...
Jeffrey?
Yeah, my view is that, my observation is that software tends to work when it works and fail when it fails, right? Which is to say that as engineers, right, it sounds banal, but it's actually, there's something to it.
Where did you get that?
Right? As engineers, we're very optimistic, right? So we code all the paths assuming everything's going to work. But then if something happens in the real world and something goes wrong, then those code paths get exercised, and oddly enough, they tend not to work and things go pear-shaped. So transactions are just a wonderful way to try and say, hey, it's either going to work or it's not going to work. You know, if you have to, in my world where you manage systems, if you have 10 things to do, if you do none of them or 10 of them, that's a good thing. If you do 7 of them and then something goes wrong, in general, that's a bad life, right? So transactions are desirable whenever possible.
Let me just
But
pile
not often
on.
possible.
Let me just pile on transactions. They're great. Do not wait until a language supports them for a particular scenario. Do not wait until they're supported by some tool for data in memory. If you can use one, great. But every method you ever wrote on an object had better be a transaction that takes the object from a consistent state to another one, including the failure case, which is what every course on exception safety comes down to, is just the atomicity of rollback and viewing every state change, every method on an object, every locked region, lock, do stuff, unlock, as a begin transaction, do stuff, commit, and if error rollback. And every exception safety talk you ever heard is about how to get if rollback right. We should be doing that today already.
I'm going to just pile on to you. I completely agree. And if you're a .NET programmer, which everyone in this room is a .NET programmer, you just may not know it yet. We did, I think, a lot of really good work in .NET 2.0, which we keep building on, which was System.Transactions, which was the in-memory transaction manager, which federates with both SQL Server in a very optimized way. So I can actually have in-memory transactions that compose with my database transactions without incurring any two-phase commit wire protocol. But then we have this very nice fluid upgrade path where if you're talking to 2 or more resources, databases, or other things, we actually promote and do DTC and do all the standard wire protocol stuff. So again, the System.Transaction stuff's like 4 years old, so we don't talk about it at PDC anymore. Because that's the way we are.
How many people use it?
A lot of people use it.
That's good.
Yeah. No, it's actually, if you're a WCF user, it's integrated into WCF, so it's pretty easy to get to.
PowerShell?
PowerShell uses it, so. In fact, last time I checked, we did a transactional file system in Vista, which again, we don't talk about because it's last year or 2 years ago. PDC is about what we're doing this year. So there you go.
Yeah, I mean, this is the whole point of transactions, is that when anything goes wrong, the transaction turns it into a no-op, which is exactly what you want it to do. The biggest problem with transactions is, to first approximation, they have to be small. Big transactions don't work because, very roughly speaking, they hold locks for too long and causes too much contention. So one of the earliest applications of transactions that I was involved with, we built a database library at Xerox PARC in the late 70s, and Dave Gifford used it to build a calendar system. And he made the entire process of making a calendar entry into a transaction, and he discovered that that doesn't work because it's too big.
Let me just disagree, because we're supposed to disagree,
Yes,
right?
of course.
Eric asked us to be at each other's throats. It's just hard because we love each other so much. But transactions should be small. I completely buy that. But let me play devil's advocate. Transactions should be small except when they shouldn't. And in particular, in particular, transactions should nest. They should compose. we need to be able to take a top-level menu click from Joe user that says, please turn on edit mode or whatever it is, which might execute 2 million instructions. And that had better be a transaction that takes my system from one valid state to another one. So yes, especially when you talk about locking and exclusivity, we really want transactions to be small when they hold exclusive access on something. But they'd better compose to something very large so they can express all the rich software we need to build. And every step had better be consistent. And the thing had better scale from very small to very large. Otherwise, we can't build reliable software. And I know you know this, but I thought I'd throw that in just as because big transactions matter too.
So can I move the topic a little bit beyond transactions? So a few interesting remarks on the stream here, and that I want to tie in, is we talked about errors and state and things like that. So what about, can type systems help us to deal with state and maybe errors? Like, for example, should the type system tell you that a method might fail? Or should we go to a more dynamic type system and say, you know, if something fails, like in PowerShell, you know, the pixie dust of dynamic typing will come in and fix everything?
Oh, I'd actually like the type system to tell me if my software is going to make me over $100 million. I mean, I really want a very rich type system that can add a lot of value.
I'm not sure that was helpful. Yeah, this is one of the classic debates, right? Oh, you know, should you declare what your error states are going to be? And the question is, well, what's the level of that contract, right?
Yes.
And that then says, well, if you then depend upon that, and someone then revises that component, and they have some new error states, well, you broke the contract. So, you know, it's desirable, just not particularly. It leads to brittle software, I think.
Go ahead.
Well, if it's a system that's supposed to be highly dependable, they shouldn't do that. Because it will break.
Yep.
I mean, and the fact that the type system is pointing out to you that it's going to break, is that good or bad? Well, you know, if you're running some flaky web app, it's probably bad because you don't really care. There's lots of other reasons why the thing might crash anyway. But if the system is actually supposed to work, then yes, of course it should tell you. It's better to know now than later.
Yeah, so I think the type system should certainly point out to you, point out to the programmer, as many ways as the method you're invoking or the service you're invoking or whatever it is can fail, so that you can either recover from that, pursue an alternative course in your software, or abort the transaction that you're in the middle of, or whatever the heck it is. And so I think the type system can help, you bet.
Yeah, you know what, to your point, I think the answer is there are different types of software, and certain software needs, different types of software need different things.
Absolutely.
So, yeah.
Absolutely. A good way to think about it is something that Jim Morris said many years ago. A type system is a Neanderthal program verifier. It can do certain kinds of proofs about certain properties of your program. And the bad thing about it is that the kinds of things it can prove are quite limited. The good thing about it is that you don't need a theorem prover. It runs as part of the compiler. And you should take advantage of that.
But that's for static type systems.
Yes.
Yeah, dynamic type systems, that's not all the case. Dynamic type systems are the way that you deal with the real world. Like the real world is messy, right? The real world, things change all the time. The real world, I took a dependency on you, and then all of a sudden you got inspired or you got stupid or something, but you changed your software. And you know, sometimes maybe I want you to break me, but for my guys, no, they don't want that. They want to just keep on trucking.
That's right.
I was only sort of joking earlier. I guess I'm with Jeff. You know, ultimately, there's lots of properties that we could extend our type systems to be able to capture all kinds of more information. But at the end of the day, you know, people still need to write a program and get something done. And I have enough experience now having richer specifications in systems to know that being able to say a lot with a little is a big deal. And I worry about, you know, I guess I become a believer in the whole, you know, my verification is actually written as other programs against the results of my own programs, which is kind of the TDD style. You know, I kind of have wondered why we don't make it easier for us to actually ship our tests with our software. So that when we have bits on a user's machine, we can actually just say, well, why don't you run the unit test and tell me how it works? And why don't you run the integration test and tell me why it's failing on your box? right?
Watch that space, baby.
So
no, I
tell
can't,
us,
I'll get
Jeff.
fired. But watch that space. It's a great idea. Well, I'll tell you about the past, right? So VMS. VMS had this wonderful system, right, where you could run what they called operational verification tests or installation verification tests. You install something, and then you can run a set of tests to say, hey, did it install? Is it operational, et cetera? And the great thing about that is, then if you make a change, like, say, for instance, apply a patch, then you can go run these installation verification tests again, and then you didn't know that everything worked, but you knew a whole bunch of things worked, and it gave you some degree of confidence that that patch was good. I'm not talking about the future, but I'll just make the observation that that was a very nice world.
So Butler, of course, is completely right, as he always is. And when you talk about the type system, though, it gives you guardrails. It lets you, it should make easy things easy to say in a language, and bad things harder to say. And it can't do it perfectly. And so you get Neanderthal analogies and things like that. But when it comes to knowing the limitations of any tool, just to throw a dart at it, type systems have great limitations. You talk about type safety. We talk a lot about type-safe languages. We use a very somewhat watered down definition of type safety when we talk about all the type-safe languages. Because, for example, to me, what real type safety would be, just in a plain Jane OO language, is that I cannot use an object that is during its valid lifetime while its invariants are met. That is, I can only call a method on it if it's a real object that obeys its invariants, which means it is completely constructed and not yet torn down. And the type safety definition that we tend to use is that you get a pointer or a reference to an area of memory tagged with the name of this will be or has been or is going to be occupied by a widget. And you can use before construction, you can use after dispose, destruction, finalization. You can get double delete in garbage collected languages just as much as in native languages that don't have GC. So be aware of the limitations of it, because nothing is a panacea. Type safety, type systems, great, but don't rely on them for everything. Nothing is perfect.
So maybe we can kind of take a little detour here. There's a very interesting talk that Tony Hoare gave a little while ago about the $1 million mistake, or maybe the $1 billion mistake of null pointers. And you kind of touch on that here too. So, is there anything that C++ makes it really easy to kind of, confuse zero and null pointers? Is there anything that you guys are doing about that?
Well, I suppose you could design a language that doesn't have pointers, but then it's odd that you still have a null pointer exception. But we won't go there. The reality is that C did bad stuff to us, but it did stuff that was useful. And therefore, even the capacity in your language of distinguishing between the reference and the thing that is referenced, which is hidden by many languages, is actually very valuable, especially when you care about higher performance programming. The more abstractions you pile up on something, the more things you can do automatically, the more guardrails you can build in, but you get that much further away from the machine. I mean, we're already how many levels away from the machine to begin with. The programming language will add that much more runtime on top. But to the extent that we can get to safe code, whether native or managed, and be able to protect ourselves against type errors and against memory errors. Type and memory safety is the way of the future. Certainly any interesting language that comes along would have to have type safety and memory safety in order to be interesting to mainstream programmers, especially in our security and reliability conscious world. And you can write lots of safe code in C++ and C, but you do extra work for it. At the same time, anything in the future is going to only do better than what we have now. And there's a lot of room in all languages to do better.
So to talk a little bit more about...
Oh, Butler and I, before we were having this conversation, I thought I'd offer him the opportunity to refute the assertion that everything going forward is going to be better than in the past.
Yeah, I was just telling Jeffrey, he was telling me that he's going to redo something. Don't tell him what. I wouldn't dream of telling him what. He's going to redo something. And I said, well, in my experience over the last 30 or 40 years, that thing has been redone 4 or 5 times. And as far as I can tell, there's been 0 improvement as a result of those 5 redos. So you should be careful to make sure that you have a clear path to improvement for the 6th redo.
So to continue a little bit on the notion of pointers, I want to take it in a slightly different direction. If you think about pointers, right, you're getting some data or something from somewhere else. So the step from referencing your own memory to referencing another machine is not that big. And so we know we all try to do transparent distribution and things like that. Should pointers be like, explicit to follow, or what do you think about, like, how should we treat distributed programs? Should we make the boundaries clear, or should we try to hide the boundaries?
Bjarne Stroustrup and many others have talked about language design and systems design and made the same basic point, that differences that don't matter should be hidden. Differences that do matter should be surfaced in the user's face so he sees them. Boundaries are one of the most expensive things. Any boundary, crossing any boundary, has some expense, whether it's native managed local, whether it's local box or remote box. And so I would say always make the boundary transitions visible, otherwise you're setting yourself for performance and correctness pitfalls.
Better be careful, so you want the boundary between cache and RAM to be visible too.
Yes.
Come to my effective concurrency talks.
Well, the difference is that the path between the cache and the RAM rarely fails, but the cache between two machines, the connection between two machines is the least reliable component of the system, always has been, is, and always will be the least reliable component. So that's a boundary I think you want to pay attention to.
I strongly agree with this. I feel very comfortable saying this since I did a lot of the early work on RPC. I'm pretty confident that the net contribution of RPC to human welfare has been negative.
Yeah, I don't like the idea of making references to especially mutable data across address spaces. I've been a fan of shared memory all my life. To me, that means one address space in which everything that wants to communicate via memory exists. And if you're not in that shared address space, then we need to go into functional style send messages, not RPC probably, but something that lets us pass values around instead of trying to dereference something that's elsewhere. If you are trying to maintain consistency, is the word that Herb used earlier, on a distributed data structure, good luck to you. It's challenging.
So another slant on this is we have a very good and very widely deployed implementation of remote pointers today. It's called URLs. And just think about that a little bit, and you'll understand a lot about the issues.
Do you?
But you don't get consistency.
And I was going to say, are there?
Load and store on URLs either, right? I
Sure
mean,
you do. It's called get and post.
Well,
I was getting the mic only to ask.
Break anything? I bet it does. I mean, if I post something to a URL and that URL is referenced by others and they're not expecting that thing to, acquire new content from me.
They better be expecting it.
Well, right. Okay, great. So this is safe. We can use power tools. They have very sharp edges and no blade guards, but we know how to do that. I've heard this before too, Butler.
A billion people are doing it and they're happy.
Yeah, right.
Well, I dispute the last part.
Well, and look,
No, come on. 50,000 compulsive people like you and Burton are unhappy, but the other a billion minus 50,000 are perfectly happy with URLs.
If that's true, the question is, I'll throw in is just, are there more dangling pointers or dangling URLs?
Oh, far more dangling URLs. It's okay. Get with the program.
So Don, you're a REST guy, right? So tell them that they're wrong.
no, I actually agree with Butler. I long for the day when a language has URI as a first-class data type with URI literals and integrated into the pattern matching system, all kinds of stuff I could imagine doing there. But going back to what Burton asked about, yes, I can dereference a URL, but in terms of concurrency control, the access protocol has built into it the ability to do concurrency conflict detection, right? So I can actually...
On that one object. So suppose I have an interrelated set of objects that are referencing each other in various ways. Gee, this sounds like a familiar theme. I think we've been here before.
Sure. Yeah.
So I'm not worried about dereferencing URLs in general. I'm worried about mutating them. I'm worried about mutating anything indirectly, I guess. I even worry about it directly, but indirectly I really worry about it. Okay, and that's not the same as, well, there's some local property I have to conserve, and so I'm going to go take some locks or do some optimistic thing and cause it. That's fine. But I don't think as a general rule, this is something we ought to encourage people to engineer software with.
It's done.
As far as pointers
Genie's
go,
out of the bottle.
let me just make sure that I come out pro pointers. I think they're very useful. It's very important to be able to distinguish between in high performance code at least, the thing that's pointing and the thing that's pointed to. And as soon as you have pointers, you're going to have issues with that we have even today in every language: use before construction, partially constructed objects, use after destruction. And those problems are roughly the same in all the major languages.
So to go back to our stream here, and we talked about many-core and parallelism, but one of the things, and Jeffrey said that last night during dinners, my wife has a supercomputer. She has, what was it, 4,000 cores in her GPU.
250 or 512.
Exactly. So how do we kind of program these things, Burton? So how should we kind of leverage the GPUs with so many cores?
Well,
and can we?
Sure, it's underway. I think what will happen now that we've sort of hit the wall in terms of how many watts we can tolerate on the path we've been on, we're going to see not only more cores but more diversity. And I think there's going to be a fair amount of evolution in processor architecture aimed at reducing power or improving performance to power ratio. GPUs are the target du jour because graphics has been sort of the most amenable sort of use of this special purpose hardware. But I think we'll see some others. And I think we'll probably keep calling them GPUs for the next 3 decades, but they're going to take on a much more general purpose character, going to be much more interoperable with CPUs and other kinds of processors on the socket. They're going to get more interesting to Microsoft and Apple and everybody. You bet.
Jeffrey.
Yeah, no, I believe in that world, right? A world where in the future, you're not going to have a uniform space, right? There's not going to be the dominant language. You're going to have lots of things. You have lots of variety at the hardware, lots of variety at the programming runtimes, lots of variety in languages, etc. And then the interesting thing becomes, how do you glue all those components together? And so I think over time, glue becomes the critical factor. What are the great glue languages? What are great glue protocols? What are great glue mechanisms to stitch together these things? Because anybody betting on one thing, I bet you GPUs are going to take over and there aren't going to be CPUs, or I bet you, language X is going to be it, or some runtime Y. I think you're just wrong. That's not going to happen.
You started off by asking specifically about parallelism, multi-core, many-core. Just to repeat something I said on Monday, that's I don't think too much of a secret, but it is a dirty little secret. Nobody wants multi-core. The hardware vendors don't want multi-core. Yes. Us mainstream guys, Bert. Us mainstream guys. No, the hardware vendors, software, most of us would be ever so much happier if we could just keep getting chips that were twice as fast for our sequential code every couple of years. And we'd pay great money for that. And we just don't get that anymore. And so now we've got to learn to build programs a different way. But again, I really think it's important to see it as not some deeply mysterious transformation, but simply doing the same thing we did for GUIs and for objects. They exist. Have a rich set of abstractions. You don't pick them all. You pick the subset that hangs together well and that mainstream developers can adopt. You might invent a few abstractions to make that fit together well. You tool it, and each time it takes 5 to 7 years to get into the mainstream, and we're at the beginning of that curve now.
So to kind of clump together a couple of questions and to kind of relate it to this. So when Jeffrey said, we have diversity where there's like different GPUs, different languages gluing things together. That smells to me like having a managed runtime that knows a lot about things that are going on. On the other hand, if you really want to kind of go down to the bits and squeeze out every performance, you want to have full control. So what is this whole thing of native versus managed? Which one where are we going?
I thought Jeffrey was actually talking at a different level. About 3 years ago, I was at a Microsoft meeting of a whole bunch of senior engineers, and 2 guys from Amazon came and told us about what they called their service-oriented architecture. And I think it's still the way it was 3 years ago from a couple conversations I've had with Amazon people. So here's the way it works. They have several hundred internal services that are accessible over the net to, if you are running on their server farm. These are for internal use within Amazon. If somebody thinks of a new service and they can persuade their management that it's a good idea, they get to form a team. Team's about a dozen people. The team has complete responsibility for the service. They define it, they build it, they deploy it, they evolve it, the whole bit. They can change it whenever they want. Anybody can invoke any other service that they feel like. There's no notion of integration testing, there's no notion of releases, nothing like that. So the Microsoft guys, as this is unfolding, they're getting more and more upset. This can't possibly work. And they're absolutely right. If you look at the web pages that Amazon serves to its customers, I'm not talking about EC2 and all that, I'm talking about Amazon as a retailer. If you look at the web pages they serve to their customers, there are a lot of mistakes. But you know, it doesn't matter. It would be bad if 80% of what they serve to their customers is wrong. But if 5% of it is wrong, it's perfectly okay. The only page that has to be right is the one that has the orange place your order button on it. Now, this is not true for all kinds of programming. You don't want to build your airplane avionics software on these principles to take something that's at the opposite extreme. And there are several places in the middle. But for a lot of the things that we do today, you know, good enough is good enough. And I thought that that was what Jeffrey had in mind.
Well, actually, there's that, and you know, I like to study materials as a hobby, and materials have all sorts of properties, right? Some are brittle, some are ductile, et cetera. And it's not about, when you take a look at modern material designers, they're not about trying to find the uber material. They're often, what they're doing is taking and combining different layers of materials to get a synthetic composite material. And these are some of the strongest materials known to mankind. And so what you do is you say, yep, that's a great material, and then that's a great material, and you put them together and you exploit the properties of both to get a composite, which is really powerful. That's really what I was talking about.
Yeah, I think that's right. And I think what we need to do is just come up with better ways to make the lamination of the two work. There's one other observation I might like to make of a parallel computing sort about managed memory, which is, by the way, the only attribute of managed code I think really defines it. You can compile as late or as early as you want, and pointers can exist or not exist and be safe or unsafe in any language, managed or not. The thing that is special about managed code is that storage deallocation is automated. And in a parallel world, that's very important. And the reason is that if I've got a whole bunch of people partying on a data structure, how do I know when the last one has gotten out of the pool? You know, how do I know when to call free? And the answer is, well, sometimes you do. But the idea of actually being able to explicitly free storage based on the von Neumann idea of we're doing everything one at a time. Yeah, there's lots of nesting and fancy stuff, but basically instructions, you know, do their thing one at a time. That gives you a way to reason about when you should free storage. Well, if you were in a parallel world, you may not have that luxury. And so I think memory management has a strong role to play in the world of parallel computing. And Minicore, go Minicore.
So Herb, what should we have garbage collection for C++?
It's actually been proposed. It didn't make it into the current standard, but that's... people have written C++ applications that use garbage collection. We do not ship one in our box. However, it's something that's definitely of interest. And Burton mentioned some areas, like for instance, in certain lock-free pieces of code, having garbage collection is really, really important. Otherwise, you get into arcane code that Andre would love.
Yeah,
but to put a reference to somebody not here so I can take advantage of him. What was the question again?
his memory has been collected while he was speaking.
Oh, yes. Oh, yes, the garbage collection. But as much as I like garbage collection for parallel code and for non-determinism and that kind of thing, by far the most important reason is for type safety. But we're not there yet either. It's necessary but not sufficient to get to the safety level that as an industry we still need to get to and still are not at.
Is there anything you have to say about garbage collection and managed code?
Yeah, it's wonderful. It's great. You know, it's like anti-lock brakes, right? You know,
Yeah.
talking last night with some people, grew up in Michigan. Boy, back then, you know, you had to pump those brakes, and you had to be a good driver or you were going to die. And now you just like...
Wait, that explains it.
That explains it. So now you don't have to be a good driver anymore to perform well on snow, right? You just bash and the computer does all the heavy lifting for you, and it pumps much faster than you ever could, and you can steer through obstacles. So it's just, in my view, again, an application where computers help you think less, let you perform. There's this distinction, right? Vygotsky talked about activity theory, this distinction between your performance and your competence, and that certain tools allow you to perform above your level of competence. Anti-lock brakes is one such example. Managed code and garbage collection is another.
Let me just say, though, that every tool, first of all, I don't want programmers to stop thinking. I do want them to stop thinking about stuff that is irrelevant and they shouldn't have to bother with, and step-by-step cookbook construction, such as a lot of the manual memory management. But you'll see this with garbage collection as with any tool. People rely on it too much for what it's not appropriate for. People abuse it. It's a safety net that people think will keep them safe even at 100 miles an hour when it's rated at 5. So, and in particular, here's an example. When you deal with object lifetimes, with the idea of memory lifetime, great. Garbage collection is the best answer. We know how to do it well. Why not automate memory reclamation? And by the way, you can do that behind alloc and realloc and free as well. It works well behind C even. Having said that, and that's just automating the cleanup. Having said that, people have, from pre-Java to .NET and onward, have also tied, oh, well, objects are in memory, therefore object lifetime, memory lifetime. Pretty much the same thing, right? We don't need destructors, let's have finalizers. Wrong answer. Because you almost never in .NET want to write a finalizer. You almost always want to write a dispose function. Certainly if you want a finalizer at all, you definitely want a dispose function. And people have written a lot of low performance code that didn't need to be that way, that made the garbage collector look bad because they relied too much on the garbage collection for what it shouldn't be used for, namely object teardown, which is what destructors and dispose are for. But we still haven't learned that because a certain new language I saw very recently still doesn't do destructors. You'd think we'd have learned that one by now.
Yeah. But by the way, they put great brakes on cars so that you can drive faster.
So moving even like beyond like native versus managed, let's talk about modeling. Okay, so is modeling the answer? So we should stop programming and just do modeling, and then all our troubles will vanish?
No. Look, people are going to program till the world stops. Right? I saw 2012, so I know exactly when we're going to stop programming. No, look, I think I think there's a role in being able to write more stuff down about what your program should do or what your program's expectations are about the environment. You know, we've seen a steady trend for the last probably 20 years at least, I could probably go back further, of extracting more and more of the program specification out of code and putting it into XML files or .ini files or databases or wherever, or XML, XAML and config and all the other stuff. Look, I think there's a value in being able to extract stuff out of your code, but there's also value in being able to write code. So I wish it was easier to intermix these things, and we'll get better at it. But no, it's not going to go away.
But what are you doing with the stuff that you extract from your code?
People wind up writing programs that go extract that stuff and go do stuff. That's why, the modeling space, if you look at the history, it almost always winds up reducing down to getting data representations, getting a representation of some intent, which eventually someone writes a program against, right? It always bottoms out in code, right? But if I think about what the artifacts that are getting left behind are, they always bottom out in data, which is why you get this kind of weird homo-iconic action going on in the modeling in data space.
So Jeffrey, you looked puzzled when he said homo-iconic. That sounds like PhD level math.
Some kind of perversion to me.
Yeah. Where do you go with that?
Yeah. But one of the things that, if you look at what we talked before, is like when we talked about type systems and like, where we said that type systems are maybe kind of too primitive and we need to have more programs reasoning about programs. Is that something that, that modeling will give us, that we can let computers help us program better?
I know the answer to that. 42. Right? Because you're going to eventually have to build a computer bigger than that computer, bigger than that computer, and then you have one the size of a planet or the universe, and then we know what the answer to that is.
No, it doesn't tell you everything about the program. Just some things.
Yes, but I liked my soundbite.
I'll give you a competitive soundbite from Randy Bryant, who was one of the pioneers of model checking. I prove small theorems about big programs. So I can prove that this program never dereferences nil. That's a good thing to know, and you don't need something bigger than the program to do that.
Yeah, there's this statement out there that says, oh, if you put it in a model, you can reason against the model. But honest to God, I mean, people have been doing this with code for a long time, right? You generate an AST, and then you program against the AST, and we've got prefast tools and FXCOP tools. And so it's really kind of, in my view, a specious argument, right? I mean, I think the interesting thing, though, is whenever you take something that's private and make it public, and you make it public in a standard way, when you do that, you open up that public artifact to an ecosystem of people to add value. Now, if they don't, then it was no use. But if they do, that's a real value. That was one of the things about, when people started to go to some of these message-based systems. Well, one of the points about a message-based system is that, well, I'm sending messages to this guy, and I do it a private way, well, that's it. It's me having a conversation with myself. But if I do it in an open way, then all of a sudden, somebody can come in and can say, hey, you know what? I'm going to intercept that, and I'm going to send it to this guy, and this guy's going to evaluate some policy. And he's going to say, oh, between Tuesday and Thursday, the answer is no, and other than that, I'm going to pass it through. But you've now taken something that was private, made it public, and allowed a third-party ecosystem play. So that's an interesting conversation.
Yeah, I completely agree. In fact, my good friend Eric Meyer knows this one, which was what we saw with LINQ was by having a standard schema for representing fragments of programs. Can't represent the whole program in LINQ yet. Maybe we'll get there in a couple more versions. But I can represent a fairly large chunk of interesting specification by writing a LINQ query and just capturing the quoted expression tree. And we saw by having a shared schema for that model, which was a model for a functional expression, we were able to build this ecosystem around it where people were able to write different kinds of programs that were able to consume that data and do different kinds of things. In one case, we compile it down to IL and run it. In another case, we send it off to a database and execute it there. In fact, we have a couple ways of doing that, right? There's all kinds of things we can do with the peeling. By having a common rep, not going to use the M word, but by having a common representation, we can call it a model if you want, I don't care. I totally agree. That's the kind of the center of gravity.
It's been clear that the way to simplify programming languages by adding stuff to them actually works if you add abstractions and you add the right abstractions. That's really the only way that you can simplify code, by adding stuff. And this is, to me, seems like very much in that vein, where now I get to say something, not just how, but what I meant, in a way that not just the person who originally wrote the code understands, but the tools and other developers can understand. And that is clearly an important path forward.
I'm glad you said that, because to come back to the original question, I thought the whole point of modeling was abstraction.
Yes.
And abstraction in general is good.
Well, closing the semantic gap is good. The gap between what it is that I think and what it is that I express. If you can close that, that's a good thing.
And actually be able to say it in code.
Yeah. Well,
and let me just throw a less facetious answer than 42 in, and just as a pointer, if you look at communications of the ACM, it's online as well. In the October issue, so just a month ago, Tony Hoare wrote a nice retrospective. And of course, there are a few people more than Hoare who will believe in theorem proving and being able to do formal verification of programs. And it's interesting to see how he really values now this modeling, theorem proving, and testing as equal partners that together are complementary and address software correctness. So run, don't walk, and read that article after this.
So I worry about where the theorems come from. Guessing theorems is not something computers do very well. And we don't have, I mean, it's one thing to extract a model from a program that just appears on our doorstep. It's a whole nother thing to have a sort of a declarative basis for the properties and truths of the program as we write the program. And you know, I mean, so I've had experience of looking at other people's code a fair number of times in life, and the most fun I've ever had was looking at comments that actually described the invariance of the program, that really said, here's what's true about this data structure or this computation or whatever. We don't do that as much as we should, I think, and I don't think we can rely on automation to do that for us. We can rely on automation to prove those theorems, to check the models, to verify things, and it can be harder or easier depending, but if the theorems are small, then the programs can be big. But it's these kinds of input that we don't really have. Where do we get the declarative part of our discipline? Right now, we're just writing recipes, but how do we actually get the rest of the story so that over the long term, our programs are maintainable by us and others, for example?
So can I tie this back to some of the things in the stream? And by the way, I'm trying to kind of do a stream of consciousness, kind of, you know, picking out what I think is the essence of your question. So if I don't ask, you know, the exact questions, that's exactly the purpose, because, you know, you inspire me to ask the question, so it's channeled through me. I'm your your medium. But anyway, so one of the things we talked here about, like, you know, syntax, semantic gaps, and so on. So, and about modeling. So what about DSLs and text versus pictures? Should we program in a completely different way? Is you know, text just old-fashioned and you cannot express your thoughts?
No, text is awesome. Text fucking rocks. I love text. You will peel my text editor out of my cold, clammy fingers. No, look, I'm trying, especially this year, trying to use less and less of the highfalutin terms. Look, text processing is super important. I think being able to write stuff down in text is a phenomenal thing. We've seen text make a big splash in protocols. Turns out the web is built on text-based protocols. Turns out the formats we use for data interchange, the ones that are based on text, have a lot more legs. I think being able to write stuff down in text is super important, and that's why, my day job is actually making that easier to go do. Now, do people want to draw pictures too? Sure, I guess, and I think it's awesome that people want to go do that, and we need to make that good too. But look, if you grew up as a programmer, right, you learned to program in text, and we lose that at our peril.
And I think that one reason why that is so true, where we augment text with some graphics and diagrams and UML or whatever where appropriate, or some other kinds of things, but we come back to text. And I think the reason for that is because programs are for people, not for computers, primarily. Because they're us talking to express what we mean, not just to the computer, but primarily to other people who are going to maintain our code, to our future self 6 months later, who will not have any idea what I was thinking today, this afternoon, when I was first writing this code. And so actually translating it into bits is far less important to software, unless you don't care about the software and you were going to throw it away anyway, which we hope we weren't doing, otherwise we might as well start a laundromat.
Yeah, my experience is when you see these graphical programming environments, my observation is that they're always, usable when they're useless and unusable when they're useful, right? So all these demos, right? No, notice this. I'm serious. Next time you see one of these demos, notice you're going to see like 5 things on the screen, right? And they're all there. Well, 5 things. Good Lord, you could just burp that out. You don't need help for that, right? But then when you say, well, look, I've got 500 of these things, then they're completely unusable, right? You're zooming and you're zooming in and then you zoom out because you lost context. And, I think it's just smoking dope.
I agree with that completely, and I'll just add, the other thing that's bad about these graphical notations is that it's much easier than it is with text to delude yourself into thinking that you know what it means. And UML is the canonical example of that, in my opinion, where, as far as I know, no one can tell you what a UML diagram means.
But you have to admit it's much better now with rectangles than with the clouds.
Possible, yeah, a lot of reach.
Packing is better.
That's right.
Okay, so I hear not a lot of fans of graphical programming here in the audience. So another thing that comes with this when we talk about text, and we talked a little bit, Don mentioned that a little bit, but there was a question way in the beginning about that. Why do we then, I agree that I like to write my code as text too, but why do we store our programs as text? Shouldn't we store our programs in ways again, that show the structure, because at that point, the human is not involved anymore, right?
No.
It's the machine that then kind of,
No.
Good. We have no and yes.
No, I was just animated. I don't know what my answer is going to be yet. So it's been a while since I've had a chance to disagree with Butler directly. I think the answer is it depends. There's absolutely reasons why you want the source of truth to be in a linear sequence of Unicode characters. Absolutely. That's the way it turns out our source code control systems work based on text as well.
Yep.
And diffing and all those things.
But by all means, compute other stuff from it.
Yes,
And store that in
absolutely.
all kinds of ways. That's fine.
The ability to derive data structure out of text, to be able to glean it out of text, is really the holy grail, right? That to me is where I've got the ability to have data in this representation, which for a lot of applications is exactly where it belongs. Now there are times when when the volume of the data is so large that I can't pragmatically infer that stuff on the fly. At that point, it turns out I love having a structured way of writing it down and storing it. But again, you're going to pry the text rep away from, dude. I'm going to go to blows with you.
So I'm afraid that you failed in your goal of disagreeing with me. Because I subscribe 100% to all of that. And in fact, I would generalize it and I would say if you want to store something in a computer in such a way that you can have high confidence of getting it back in 6 months, there's two possible ways to do it. One way is you put it into a relational database with a simple schema. And the other way is you put it in a text file and you edit it with Notepad if something goes wrong. And those are the only two ways that you can count on.
Yea, verily.
What about the registry?
My point exactly.
All right, so let's not look too much back to the past. We have 3 minutes.
It's our present still. That's the problem.
So let me ask like that. So, do you think in 5 to 10 years, do we still have the registry? No kidding. What do you think we will be talking about in 5 to 10 years when we have this panel, when we talk about the future of programming?
I think we'll still be talking about parallel programming. But I think that's right. I mean, consider, the whole idea of doing instructions one at a time was this cockamamie idea that this von Neumann guy had, or somebody who said, we don't need these patch panels anymore to program computers because they're cluttering up the machine room, we got to get people down there to change plugs when we find bugs. It's just not very maintainable stuff. I tell you what, why don't we just store what the composition of functions that does this computation is, why don't we store it in the same memory we used to hold the numbers? And we can store it in there and then and it's true we can only interpret those things one at a time because we can't get at it all. I mean, it's in a memory of some kind of Williams tube or God knows what, right? So we can only do these things one at a time, but that isn't a problem. We can do instructions one at a time. And then we got variables, and oh my God. So we invented a bunch of stuff. We invented a bunch of stuff to make computing possible. And now we're sort of saying, well, now we need to do more than one thing at a time. So my opinion is we have to reinvent our field a bit. And it's going to take us a while. So 12 years from now, we'll still be reinventing. It'll be further, but we won't be done.
Very good, very well said. My gut reaction to your question was going to be, well, pretty much the same thing we're talking about this year: safety, parallelism, all the composability, reliability, because except for maybe parallelism, that's what we would have talked about 5 years ago, and things aren't changing that fast. We turned that big corner. However, there is one thing that's looming that we managed to evade by going parallel, and that is that Moore's Law is going to end sometime. That is going to be the biggest left turn. that the industry will face, and it's still not clear at all what happens then. Because at least now, by heroic efforts and building a new generation of tools and rewriting your code in a different way, you can still get faster programs on the same die size in a personal computer or in the same dollars, in practical terms, in the same living room corner. But once Moore's Law ends, and we think we've got another 5 or 10 years left at least, Moore's Law is not over, as much as Slashdot-threads like to say, but it's going to end sometime because you can't go exponential forever. That will be very disruptive, and that might be around the 5 years or 10 years from now when we have these panels. And then optimization will get very, very sexy again.
Boy, that'll be a big change. You know, today's PCs are approximately 50,000 times better than the Alto in every dimension. And they do maybe 50 times as much, generously. So there's a factor of 1,000 to be accounted for.
Abstractions. We pay for abstractions, and they're cheap at the price. Unfortunately, the price is going to go up. That's the only major change.
Okay, so we need to kind of finish up. We are out of time. So Jeffrey and Don, your last what?
10 years from now, we'll be talking about how to use Natal to do programming through interpretive dance.
I'm with him. I actually agree with everyone on the panel. I think the whole thing I hope is we can figure out how to solve both the programming in the large and programming in the small and come up with a reasonable model for that. Because I think there's a lot of shared problems, but the solutions probably look different.
All right. Well, thanks a lot, everybody. I hope that in 5 to 10 years we'll have another panel. So thank you very much, and enjoy the rest of the PDC. And thank you, great panelists.